Based on what we just saw, let's try a new idea. Since we said, hey, these polynomial approximations don't have the same derivatives as the function we wanted, so let's try matching the derivatives very carefully. But we're going to focus at just one point. We might pick x equals 0, we might pick x equals pi over 2 or something. We'll talk later about that. To match derivatives, we'd say we want our polynomial approximation to have the same first derivative and same second derivative and third derivative and so forth. But it would also be nice if it had the same y value, like it actually went through a particular point that we had picked. And we can think of the y value as the 0th derivative, so it kind of fits in the system here. So how are we going to accomplish that? Let's give ourselves a little puzzle here. Kind of strip away all the unnecessary stuff. Sorry, it's not an application, but not everything can be, right? So can we find a polynomial whose fourth derivative at a horizontal value of 1 is 1? So take a sec, guess what kind of polynomial, hopefully a simple one, what might have a good fourth derivative at x equals 1 that'd be fairly simple. So you might say, let's try how about x to the fourth? That probably has an interesting fourth derivative, right? If we tried x squared, that would have a fourth derivative of 0. If we tried x cubed, that would have a fourth derivative of 0. So x to the fourth seems like about the simplest thing we can reasonably try. So what about its first derivative? That's the first derivative of x to the fourth, or x cubed. How about the second derivative? 4 times, like copy the 4 and then 3 comes down in front and we get 3x squared. Third derivative, 4 times 3 times 2 times x to the 1. And then fourth derivative, 4 times 3 times 2 times 1. You could say times x to the 0, or you could just leave that off because that's 1. So the fourth derivative of what we tried, our kind of guess, was not 1, it was 4 times 3 times 2 times 1, which is 24. So can we adjust our guess to give us the derivative, the fourth derivative we want? So the derivative we got was 24 times too big compared to what we wanted. So what we could do is make it 24 times smaller than what we started with, and then maybe it would end up at the right place. So we could say, how about 1 over 4 times 3 times 2 times 1 times x to the fourth. And then what are you going to get for the fourth derivative? It would be 1 over 4 times 3 times 2 times 1 times the fourth derivative of that, which we got there, 4 times 3 times 2 times 1, and you could just leave off the x to the 0. So that all ends up canceling and gives us a fourth derivative of 1, just like we expected, or just like we hoped for when we adjusted the guess. So this is an interesting thing. If I tell you what fourth derivative I want, that doesn't just become the coefficient on x to the fourth. The coefficient on x to the fourth ends up being this complicated thing that comes from powers coming down from the power rule over and over again. What if I had wanted like 7x to the fourth? That would have to be 7 times bigger. What if I wanted a polynomial whose fourth derivative was 7? I would need something whose starting guess was 7 times bigger, so I could just throw a 7 in there. Another way to think about where this kind of comes from is, instead of guessing something and then working down to the fourth derivative, let's start with what we want the fourth derivative to be and then work back up the ladder. So we know we want a fourth derivative of 1 in this case. And how do I go up the ladder of derivatives toward a polynomial or something? Well, I just take antiderivatives. And so I could say, what's the integral of 1 dx? That would be x. I'm going to leave off the plus big C. So I just took one antiderivative. Now what's the next antiderivative? An integral of x dx gives me 1/2 x squared. Okay, I've done that twice. Let's do it again for third derivative. So integral of 1/2 x squared. Oh, not integral. I'll copy the 1/2, and x squared turns into 1/3 x cubed. And then what's the integral of 1/2 times 1/3 x cubed dx? That would be 1/2 times 1/3 times 1/4 x to the 4th. And sure enough, we're getting that 4 times 3 times 2 times 1, just like we got here. So it works whichever way we think about it, saying let's try a guess and adjust it and take derivatives to make sure it works. Or we could start with what we want and take antiderivatives and we get the same thing. So you might be recognizing this 4 times 3 times 2 times 1, that's factorial, right? So let's remind ourselves of factorials. So if we write n factorial, that's 1 times 2 times ... times n. So 4 times 3 times 2 times 1 is 4 factorial. I mean, here I'm writing it kind of backwards compared to the way I wrote it there. Either way is good. Let's explore this a little bit. What would 3 factorial be? That would just be 3 times 2 times 1. We said this is 24, this is 6. So about 2 factorial would be 2 times 1, which is 2, last I checked. About 1 factorial, that would just be the 1, right? And so then here's the question, what would 0 factorial be? Well, there's a few ways to think about it. One is, what's the most convenient thing? Turns out the most convenient answer is 1. Another way to think of it is, what do I do to go from 24 to 6? You could say I divided by 4, right? What do I do to go from 6 to 2? I would divide by 3. What do I do to go from 2 to 1? Divide by 2. And so to go from 1 to something, I should divide by, what's the pattern here? Divide by 1. And if I take 1 and divide by 1, I should get 1. So it seems odd, but it turns out the best way to define 0 factorial is that 0 factorial is 1. It fits this system. It's interesting here to ask what would negative 1 factorial be in this system? You'd say take 1 and divide by 0. Right, that's what would follow in the pattern here, and of course you shouldn't do that. So you'd get an error in Excel called div0. So you can't do negative 1 factorial, but 0 factorial should be 1. Let's think about that a few other ways that are actually mathematically interesting. You've probably seen summation notation. So if I said, what's the sum of x sub I equals 1 to 3, that's a shortcut way of writing x1 plus x2 plus x3. How about the sum I equals 1 to 2 of x sub I? That would be x1 plus x2. How about the sum I equals 1 to 1 of x sub I? That would just be x1, right? And then how about the sum I equals 1 to 0 of xi? We've kind of lost all the things we wanted to sum, so I think we would agree that's 0. If I sum 0 things, the answer is 0. Let's think about what if we're taking products. You can write a product of a bunch of things using a big capital Pi like this. You'd say I equals 1 to 3 xi, that would be x1 times x2 times x3. And then the same thing here, I equals 1 to 2, xi would be x1 times x2. I equals 1 to 1 of xi would just be x1. And then how about the empty product, I equals 1 to 0 xi? What would naturally go here? Well, 0 kind of feels like a reasonable thing, but another way to think of it is 0 is the additive identity. It's the thing that if I use it in adding stuff, I don't change what happens, right? So here I'm going to put the additive identity. I'm saying 0 is the additive identity. And so over here I should use the multiplicative identity. What's the number that when you multiply it by stuff, the stuff doesn't change? That's 1 rather than 0 for addition. So that's another reason why we should think of an empty product as having a value of 1 rather than 0. Here's another way to think of it. If you're familiar with code, this is just kind of computer pseudocode. But if I wanted to add up the numbers in some array called x, I would write a loop like this. I would initialize my variable and then go loop through the array and add stuff to my variable, and then temp sum would be my final answer. If I wanted to multiply all the stuff in an array, I would just put a star here instead of a plus. I would call it temporary product instead of temporary sum. But what do I need to start temporary product at so I actually get something reasonable? I would actually have to start it at 1, right? Because if I started it at 0, then all these multiplications would just keep giving me 0. And then if n was equal to something less than 1, this loop wouldn't happen at all. And then what would the final answer of temporary product be? It would just be whatever it started with, and then the loop didn't happen, so it would be 1. So the empty product should be 1, where the empty sum is 0. So all this is a long way of saying 0 factorial is equal to 1, not 0. So remember that.